Okay, so you guys saw series and parallel, right? Now, suppose let's say you have an inductor, you connect it to a source. See, what will be the energy stored in an inductor? Even this is also an important part, right? So, to calculate the energy stored, see, you have an inductor, you have a source. Now, the source will start sending current, right? As you press the key, so what happens? The current will start growing in an inductor. Now, as the current keeps on growing, what happens? The back EMF will also start increasing, correct? Because of the self-inductance. So, now, according to the formula, we have E is equal to minus L di by dt, correct? Now, why do we get the negative sign? It's because of the direction. So, if you consider only the magnitude, we have E is equal to L di by dt, correct? So let's call this as equation number 1. Okay, now see, the energy stored, basically the source is working because it has to send the current through the inductor, correct? And it is actually going against the back EMF. So now what we have is the work done by the source, that is stored as the energy in the inductor, correct? Right? So the work done. So let's call a very small work done as dW. Now, a small work done dW will happen in a very small time dt, correct? So we have dW is equal to, now we need to have a constant here because it's usually proportionality. We actually have dW proportional to dt. Now, to remove the proportionality, we have to introduce a constant. Now, for this, now the source, which is, so let's say some source V, it is sending a constant current of I, correct? And we have a back EMF of E. So we get dW is equal to E into I into dt. Now you guys might be thinking, why E into I? Because do you guys remember we had a formula for power? Power was what? VI, correct? So similar way here also we'll get, because we actually deduced power by the amount of work done. Similar way we use this also. Okay, now coming back to the derivation, we have dW is equal to EI dt. Now what was E according to equation number 1? So that was nothing but L di by dt. Now substitute that here. So we get dW is equal to Li into di by dt, correct? Now there is one more thing, one more very important thing, you have to integrate. Now when you are integrating this, see, one thing what you guys have to notice is dt will get cancelled, correct? Right? And then di is the only thing what remains, meaning you are integrating this with respect to I, the current. Okay, so see, the current starts from 0 and it reaches a maximum of I, correct? So if you substitute this, we get integral of dW is equal to L integral of 0 to I into I di. Okay, so if you integrate this, you will get this as W is equal to half Li square. Alright, so now you get this as half Li square. Now the work done is nothing but the energy stored in the inductor. So let's call this as U. So U is equal to half Li square. Now half Li square is the energy stored in the inductor. Since it is energy, the SI unit will become joules. Okay. Now few things you guys have to remember in this. See, the first thing is the energy stored in an inductor. This is stored as magnetic field lines. Okay, so the energy, whatever the electrical energy the source is sending, that stores as magnetic energy. Okay, now the second point is, see, suppose let's say you have an alternating current. Okay, now in the positive half of the cycle, the inductor gets charged. Okay, in the negative half of the cycle, the same, whatever the energy which is being stored, that is dissipated. So in one cycle of an alternating current, the net energy, or you can say the net power, becomes 0. Okay, now there is, in the next chapter you will see how the net power becomes 0 in an inductor. For now, if you guys know this much, that's enough. Okay, so this is the formula for the energy stored in an inductor.